Hi everyone, this is a secondary video for continuity. We'll be going over a couple examples, and this is continuity on a calculus level. So again, here are 3 steps for proving continuity. The first thing that must happen is that f of c must be defined. That means you'd be able to plug in the value of c and get a value out. The second thing that needs to happen is that the limit as x is approaching c must exist. To prove this, we need to prove that the limit from the left equals the limit from the right, and if that's the case, then that is the limit. The third and final step is that whatever values you get for your step 1 and your step 2, so the function value and also the limit, those 2 values must be equal. So here we are with an example problem from our last assignment on continuity, and this specific problem is asking us to figure out whether or not this function is continuous at a specific value, so at the value of 2. So 2 will be our c value for this problem. It's also asking that if there is a discontinuity, is it a hole, a jump, or an asymptote? Okay, so let's talk about what we need to do here. So here you can see I have my problem and I have the 3 steps that I need to show. So this is a great way that if maybe you're not too certain on how to go with a problem like this, get these pieces filled out for you to start with. Then you can work on step 1, work on step 2, and then you get it. You're on step 3. So the first thing we need to do is to prove that f of c is defined. So to do that, we basically just have to plug in our c value. Our c value was 2. So when we're plugging into a piecewise function, and it is important on what piece you're plugging into, we see that for if our x value is less than or equal to 2, we'll use our top piece. If it's greater than 2, it'll be our bottom piece. So we're plugging in 2, it's equal to 2, so we're going to be using 2x minus 3. So you can see I'm going to have f of 2 equals 2 times 2, that's my x, minus 3, which is 4 minus 3, which is 1. So our first step's completed, plugging in our c value and hoping that you get a value in return. So the second thing that we have to do is to find the limit. So to do that, and specifically to do that for a piecewise function, you need to make sure you find the limit from the left and also the limit from the right. So here we go. We have the limit as x is approaching 2 from the left of our function f of x. So again, thinking about the values of x here, when x is to the left of 2, you can see up here, this is when x is less than 2. So less than is to the left. So we're going to be using our top piece. So we'll be saying, okay, this means you're going to be finding the limit as x is approaching 2 from the left, and that function piece was 2x minus 3. So I plug in my 2 here, and I get 1. Now we also need to find the limit from the right. So we're going to be finding the limit as 2 approaches from the right of our function f of x. So we need to figure out what piece to use. Again, this is important to make sure that you're using the right piece. The values that are greater than 2 mean that those are the values that are going to be to the right of 2. So we're going to be using our bottom piece of our function. So it's just going to be x squared. So we end up with 2 squared because 2 is replacing our x, which is 4. So this kind of causes a problem for us. The issue here is that these must be equal for our limit to exist, and they're not. So the limit as x approaches 2 of f of x does not exist. Okay, and the reason why is that the limit from the left, so limit as x approaches 2 from the left, does not equal the limit from the right. Okay, so there's your reasoning there. So our limits were not equal. That's a big problem for us right now because for our final step here, for the problems that we're working on, we're trying to hope that our value from step 1 and our value from step 2 are the same. And clearly they're not because our limit does not exist. So what we can think about down here is that we would want to have our limit as x approaches 2 of f of x equal, here we go, f of c, which is 2. And for us, it didn't. Okay, so the problem with that is that when they're not equal and they don't have the same value or they don't still have a value at all, then it's going to be discontinuous. Okay, so we can write this out kind of as a whole thought here. So since the limit doesn't equal the function value, f of x is discontinuous at x equals 2. Now for us specifically, this asks what type of discontinuity, and you can see that just using these values right here, you can see that it's going to be a jump discontinuity, because on the left side of 2 we're at 1, the right side of 2 we've jumped to the value of 4. So this is a jump discontinuity. Okay, and one final example that you might see often for continuity here is finding a specific value that will make this function continuous at a specific value, and that's going to be at -3. So you can see that that's really where our pieces are alternating, and that's really where we're either going to have when x is not equal to 3, this is what's going to be graphed, or when x is equal to -3, this is what's going to be graphed. So our goal is that whether or not it's the not equals to and equals to, or less than and then greater than, we want our pieces to kind of match up, or we want our pieces to be equal to each other at x equals -3. So what we can do to get this set up is we're going to take our two pieces. We'll have x squared minus 3 equals k. These were our two pieces. We set them equal to each other. Now our problem is we have two variables but only one equation. We have x and we have k, and we're trying to solve for k here. Now if you think back to the question being asked of us, it was asking us about what's going on at -3. So that means that my x value is -3. So I'm going to have a -3 squared minus 3 equals k. So now we have one variable, one equation. We can solve this. So we have 9 minus 3 equals k, 6 equals k, and this problem is complete.